In today's video, we study the precise definition of the limit. As we did when we studied intuitive definitions, we begin with just the standard limit. So let f of x be defined for all x that is not equal to a over an open interval that contains a. Let L be a real number. Then the limit as x approaches a of f of x is equal to L if for every epsilon greater than 0, there is a delta greater than 0, such that if 0 is less than the absolute value of x minus a, less than delta, then the absolute value of f of x minus L is less than epsilon. Now this is sometimes referred to as the delta epsilon definition of the limit, right? Because it uses the Greek letters delta and epsilon. Now, what is this really saying? Well, let's take a look. If we have the graph of a function, let's say something like this. Right, we'll say this is A, and we'll say this here will be L. Right? Then what this is saying is essentially, given any value of epsilon, there's an epsilon band. So this would be L plus epsilon. This down here would be L minus epsilon, right? So we can draw a line. That would be L plus epsilon. This here would be L minus epsilon. Right, then we can find a delta. Give us a delta band. Let's say this here is a minus delta. This here would be a plus delta. Right, then this would come up. Look at that. This would come up. Look at that. And that was almost too perfect, right? So, given any epsilon, we have an epsilon band of values. We can find a delta, essentially, that gives us a delta band of x values that satisfy this epsilon band. And of course, this would be the limit right here. And what we can do is, if we shrink this epsilon band, right, so if we make this smaller, then this delta band would also be shrinking. Let's now look at the one-sided limits. So again, this let f of x be defined for all x not equal to a over an open interval containing a. That's going to be sort of a standard. Let L be a real number. That's also going to be kind of a standard. So limit as x approaches a from the right of f of x is equal to L if for every epsilon larger than 0, there is a delta larger than 0 such that if 0 is less than x minus a less than delta, then the absolute value of f of x minus L is less than epsilon. Now, the left-handed limit is going to be very similar. Except now, it'll be negative delta less than x minus a less than 0. Then f of x minus L absolute value is less than epsilon. Right now, this makes sense, right? Since we're coming in from the right, all the values of x will be larger than a, so this should always be positive, it's x minus a. Since we're coming in from the left down here, all the values of x are less than a, right? So this difference will always be negative. Now, the limit as x approaches a of f of x equals infinity if for every m larger than 0, there is a delta larger than 0 such that if 0 is less than the absolute value of x minus delta, x minus a less than delta, then f of x is larger than m. Alright, so what this is saying is that no matter how large of an m we are given, we can find a delta such that whenever x is within delta units of a, then f of x will be larger than m. Likewise, limit as x approaches a of f of x equals negative infinity if for every m larger than 0, there is a delta larger than 0 such that if 0 is less than the absolute value of x minus a less than delta, then f of x is less than negative m. And the same idea, no matter how large of an m we are given, we can always find a delta such that whenever x is within delta units of a, f of x will be less than negative m. Now, the limit as x approaches infinity of f of x is equal to L if for every epsilon greater than 0, there is an n greater than 0 such that for all x larger than n, the absolute value of f of x minus L is less than epsilon, and this is known as an epsilon n definition. finally, limit as x approaches negative infinity of f of x is equal to L if for every epsilon greater than 0 there is an n less than 0 such that for all x less than n, the absolute value of f of x minus L is less than epsilon. Right, so what this first definition is saying is no matter how large x is, we can choose an n such that f of x is always within epsilon of L. And same idea here, no matter how small x is, we can always choose an n such that the f of x is always within epsilon units of L. We will conclude this video by looking at two examples of using the definitions to prove limits, and then proving the sum law for limits. So first, let's look at this limit right here. Right, so we want to prove this. So proof. We always let epsilon greater than 0 be given. Right? What we want to show, that there exists a delta larger than 0 such that the absolute value of x minus 1 less than delta implies that the absolute value of 2x plus 1 minus 3 is less than epsilon. So what we do is let's start with this value right here. This absolute value of 2x plus 1 minus 3. Well, that would be the absolute value of 2x minus 2, which is the absolute value of 2 times x minus 1. Using the properties of absolute values, this is the absolute value of 2 times the absolute value of x minus 1. But the absolute value of 2 is just 2. But now, we're assuming that this absolute value of x minus 1 is less than delta. So this would be less than 2 times delta. Now remember, we want this to be less than epsilon, or we want this value here to be less than epsilon. So if we take delta to be epsilon over 2, we get the absolute value of this 2x plus 1 minus 3, which we just showed was less than 2 delta, is now equal to 2 times epsilon over 2, which is equal to epsilon. So now this value is less than epsilon, which is what we desired. And so that proof is complete. All right, next, let's look at this limit. And again, we want to prove it. Again, let epsilon greater than 0 be given. We want to show that there exists a delta larger than 0 such that the absolute value of x plus 1 being less than delta implies that the absolute value of x squared minus 2x plus 3 minus 6 is less than epsilon. So this absolute value is the absolute value of x squared minus 2x minus 3. Now this can be factored into x plus 1 and x minus 3. And again, using properties of absolute values. Now, this value right here, this absolute x plus 1 is less than delta, so this would be less than the absolute value of x minus 3 times delta. Now we have a problem. We want to show that our choice of delta is independent of the value of x. And right now it's not. So we want to somehow get rid of this absolute value of x minus 3. Well, since we're assuming delta is probably going to be small to begin with, let's just go ahead and assume that delta is less than or equal to 1. If we do that, then the absolute value of x plus 1 is less than 1, right? Because we're assuming that's less than delta. So if delta is less than or equal to 1, then this whole thing has to be less than 1. But that would mean that negative 1 is less than x plus 1, which is less than positive 1. Which would mean that negative 2 is less than x, which is less than 0. We're just subtracting every part of that inequality by 1. Now subtract everything by 3. Right, and the reason to do that is because we wanted this x minus 3, right? However, this is not equal distance, right? We can make it equal distance. I'm sorry. Keep it that way. This would mean that the absolute value of x minus 3 is going to be between 3 and 5. Right? Which means that the absolute value of x minus 3 is less than 5. That's the important piece here. So with that assumption, we now have the absolute value of x squared minus 2x plus 3 minus 6 is less than the absolute value of x minus 3 times delta, which we can now say is less than 5 delta. Now again, we want this to be less than epsilon. So it would seem to make sense, like we did in the previous example, to just take delta to be epsilon over 5. However, there's a problem there. We were assuming that delta was less than or equal to 1. Now this idea works. This work here works out if delta is equal to 1. So as long as epsilon over 5 is 1 or less, then all of this work is fine. If, however, epsilon over 5 is larger than 1, then this entire argument breaks down. So what we have to do is take delta to be the minimum between 1 and epsilon over 5. Right, and now, if we take delta to be that minimum, this gives the absolute value of x squared minus 2x plus 3 minus 6 less than 5 delta, which will be guaranteed to be less than epsilon. Right? Again, because if epsilon over 5 is the minimum, then this becomes 5 times epsilon over 5. I'm sorry, this should be... Yeah, I want to keep it as less than or equal to, actually. Right? Then this would equal epsilon. Right? If, however, 1 is smaller, then that would mean that epsilon over 5 is larger than 1, which would mean that epsilon is larger than 5. So then 5 would be less than epsilon. In either case, we get our desired result, and so the proof is complete. Now recall from a previous video that we said if the limit as x approaches a of f of x was equal to L, and the limit as x approaches a of g of x was equal to m, then the limit as x approaches a of f of x plus g of x was equal to L plus m. Right, this was known as the sum law for limits. We will now go ahead and prove this. Let epsilon greater than 0 be given. Then there have to exist two deltas, a delta 1 and a delta 2, such that the absolute value of x minus a being less than delta 1 implies that the absolute value of f of x minus L is less than epsilon. Specifically, if it's less than epsilon, we can say it's less than epsilon over 2. That is by this limit here. And the absolute value of x minus a being less than delta 2 would mean that the absolute value of g of x minus m is also less than epsilon over 2, which is less than epsilon. Now, take delta to be the minimum of delta 1 and delta 2. All right, so we're going to choose delta to be the smaller of delta 1 and delta 2. Notice this means that if the absolute value of x minus a is less than delta, then the absolute value of x minus a is less than delta 1 and less than delta 2. Furthermore, if we look at this, the absolute value of f of x plus g of x minus L plus m. Well, we can regroup these however we want, so we can write f of x minus L plus g of x minus m. Now, we use the triangle inequality to say this is less than or equal to the absolute value of f of x minus L plus the absolute value of g of x minus m. So the triangle inequality, let's write it up here. Triangle inequality says for all real numbers x and y, the absolute value of x plus y is less than or equal to the absolute value of x plus the absolute value of y. This is a property of real numbers. All right, so that's what we did down here. But since the absolute value of x minus a is less than both delta 1 and delta 2, this value right here is less than epsilon over 2. And so is this quantity. All right, epsilon over 2 plus epsilon over 2 is equal to epsilon. So we have now shown that when the absolute value of x minus a is less than delta, then this quantity right here is less than epsilon, which is exactly what we wanted to prove. And so the proof is complete, and that proves the sum law of limits. The other laws of limits, while not identical to this, are done in similar fashion. And so I'll leave those to the viewers to prove. That concludes our video on the precise definition of limits. That also happens to conclude our videos on the limit. So in the next video, we will start to study the derivative